Find the Taylor series and find its radius of convergence. We'll do two of these. First, f of z equals e to the z, center at pi I, and second, f of z equals log z, center at I. So in both cases, the Taylor series for a given function looks like summation k equals 0 to infinity. Coefficient z sub ck times z minus the center z0 to the k. So the centers are given. We have to find ck, and Taylor's formula tells us that ck, the kth coefficient, is the kth derivative of the function evaluated at the center divided by k factorial. So in the first case, f of z is e to the z. So fk of pi I, the kth derivative of pi I, well, the kth derivative of e to the z is just e to the z. So it's e to the pi I, which is -1. So c sub k is -1 over k factorial. And the Taylor series is e to the z equals summation k equals 0 to infinity of -1 over k factorial times z minus pi I to the k. And it might look nicer if we put this minus in the front. For the second one, the function log z has as its derivative 1 over z. And then the derivative of that is -1 over z squared. And let's calculate a few derivatives here until we can find a general formula for the kth derivative. So the second derivative is going to be -2 over z cubed. The third derivative, no, this one's going to be a plus, because this is negative z to the -2. Power rule, bring down the -2, it becomes a 2, z to the -3. So then we get negative, the next one is -2 times 3 over z to the 4th. And the next one, the fourth derivative, is equal to the fourth derivative. This one was f double prime. This one's f triple prime. This one is the fourth derivative. Okay, I lost track there because I mislabeled this one. Again, the function is f of z. The first derivative is 1 over z. The second derivative is -1 over z squared. The third derivative is positive 2 over z cubed. The fourth derivative is negative, what amounts to 6 here, over z to the 4th. I think we can write a general form now for the kth derivative after having 4 of them. The kth derivative is, it looks like it alternates. So we have -1 to the k. Is it k, right? Or is it k plus 1? The first derivative is positive. The second derivative has a minus. So maybe go with k plus 1 so that if k is even, we get a minus. And if k is odd, we get a plus. So this is our alternating symbol. And then we have a numerator, which looks a little bit like a factorial. The next derivative will have a 4 there. So this is like 3 factorial there. So that's, if k is 4, this is k minus 1 factorial. And then we have divided by z to the k. First derivative z to the first, second derivative z to the second, third derivative z to the third, etc. So there is our kth derivative. Now we're going to use this formula here. We need the kth derivative at z0. So fk at the center for the log function was I. So that would be, and we want ck. So we want to divide this by k factorial to get ck. So kth derivative at I, the center was I. So that's negative 1 to the k plus 1 times k minus 1 factorial divided by I to the k. And we also have z to the k on the bottom, and we're plugging in we also have k factorial on the bottom, k factorial. So this is negative 1 to the k times negative 1 divided by I to the k. And then the factorials, k minus 1 factorial over k factorial, just gives us k on the bottom. So this is negative for this negative here, and we have k on the bottom, and we have negative 1 to the k over I to the k. That's the same as negative 1 over I quantity to the k. And 1 over I is negative I. So negative 1 over I is just I. So this is I to the k. So these two together here make I to the k. So there's our coefficient. Negative, because this was negative 1 to the k plus 1, so we had an extra negative. And then the negative 1 to the k, I to the k makes just I to the k on the top. And so the series is, so there's our coefficient ck, as we said here. Let's put that in the little box. And now make log z centered at I, ck z minus I to the k, and there is ck. So this is, well, I think we're going to have to start at 1. We can't start at 0. Well, C0 would be the log of 1, which would be 0. So C0 is 0. So the non-zero terms starting at 1, we have negative, and we have I to the k over k times z minus I to the k. Now this one, the radius of convergence, if we could use the rho from the root test. So we have to calculate this limit, the kth root of the modulus of ck. And that's just an ordinary limit of the kth root of the modulus of ck is just 1 over k, and that's 1. So rho is 1 over 1. So the radius of convergence is 1. So the log function has a power series centered at I, and the radius of the power series is 1. So it's a disk of radius 1 centered at I. We know that the log is not defined at 0, and therefore the radius of convergence, the disk of convergence, can't include 0. So it's as big as it could be without including 0. And as far as the e to the z above, that radius of convergence is infinite, because we have this k factorial here on the bottom. And if we use the ratio test on that one, let's go back to that one for a second. Rho is 1 over L, where L could be the lim sup. We're just going to need limit again of ck plus 1 over ck. And this is going to be 0, and so rho is going to be infinite. And it's going to be 0 because this is the limit as k goes to infinity of 1 over k plus 1 factorial divided by 1 over k factorial. And when you multiply these fractions together, k factorial over k plus 1 factorial leaves us with 1 over k plus 1, and the limit of that as k goes to infinity is 0. So rho is 1 over 0, which we treat as infinity for the situation involving the radius of convergence. So this one converges disk pi I radius infinity. We don't write that, we just write everywhere on the complex plane. And this one, the log, we did have a very particular disk of convergence centered at I, radius 1. So those were the disks of convergence. So I believe we found the Taylor series and the radius of convergence for both of these functions. For e to the z, this is the series, and it converges everywhere. And for log z, this is the series, and it converges only on disk centered at I